Hello everyone and welcome to our lecture on inductance and capacitance. This lecture is going to focus on inductance and we'll go to capacitance on the next lecture. So again, welcome to inductance and capacitance. In this first part of this lecture we will cover the equations for voltage, current, power, and energy as it relates to inductors. We'll discuss how an inductor behaves with a DC direct current. We'll discuss continuity requirements for an inductor. We'll review combining inductors in series and parallel, which you have already covered. And in the second part of this lecture, which will be on a different video, we'll cover the same objective as discussed for inductors, but as applied to capacitors. Okay. So inductance, what is it? Inductance is, by definition from your book, is a linear circuit parameter that relates the voltage induced by a time-varying magnetic field to the current producing the field. So in this course, we are only covering DC, direct current, so we will not dive into AC, alternating current, until your next course. Let's break down this equation into its basic parts. Whenever you see the V and T with a T in the parentheses like that, it means that the voltage is dependent on the unit of time. And we say V of T is how we actually would pronounce that. Therefore, we say it is time varying. The symbol for inductance, the inductance unit is in this equation is L, and is measured in a unit called henries. And finally, the last time varying variable is current, represented as I of T, I with the T in parentheses. Again, the parenthetical T means it is time dependent, but also that it is related to a function of T. So in algebraic terms, this means I of T is represented as an equation. The other part of this inductor equation, which you see as d something over dt, just means that we take the function of I of T over T as a rise over run of the function, and that's basically what a derivative is. So if we were to graph this function di of t over dt, so I'm just looking at that, what looks like a fraction to you, d of I of t over dt, we would be graphing the rate of change and not the actual value of I of t. So comparing a graph of the change in I of t and overlap it with d of I of t dt, we'd find that the latter term is the tangent to the first function's graph. And I'll break this down into algebraic terms so you can work out the math you want to see this function to that level, if you want. Okay. So here we're asked the question, look at the inductor equation. Suppose I of t is constant, then V of t is equal to what? And of course you have the answer equal to 0, but let's go ahead and work that out in concepts so that you can understand what's actually happening. So let's discuss some larger concepts using the previous equation as applied to inductors and what we know of them so far. If you were to keep current constant, what happens to the equation? Okay, so knowing that d of I t over dt is looking for a change in current over time, and if the change is constant, meaning the numerator is 0, there is no change. It doesn't mean there's nothing there, it just means that the change hasn't changed. That's all we know. And so the whole variable becomes 0. And why is that? If you multiply L, which is the inductance in that equation, by 0, you get V of t is equal to 0. And so if I missed this, if I didn't actually, if you need me to re-say this, the top part, if we don't have any change, we know the change is equal to 0. So any fraction where you have the numerator equal to 0, you know that whole variable goes to 0. So d of I t over dt goes to 0, and there is no change. And so calculus isn't that much different from algebra. Okay, so here we say, so if the current in an inductor is constant, its voltage drop is 0. We already proven that mathematically in the previous equation. So the inductor can be replaced by, and again we're given the answer, a short circuit. You also have the options of an open circuit or a capacitor. So now let's think about this further. If the current in the inductor is 0, then B, just using regular Ohm's law, equal to I times R, voltage must be zero. Because if current is zero, voltage is zero. So just using regular Ohm's law will tell you that you have to have zero voltage. So this is the equivalent to looking at the inductor when using DC direct current as a short. Okay, so let's look at the physics phenomena and what you would expect from the equation not being possible in physics. So if current is constant, we know that the inductor has no voltage drop and is essentially a short. So we've already kind of proven that in the last couple of slides. Suppose that the current was to make an instantaneous jump to another value. So in essence, let's, sorry about if you heard that announcement. I'll shut off my announcement so we can do that again. Where was I? So suppose that the current was to make an instantaneous jump to another value. So like in essence, it says 0 amps at the beginning, but like a square wave, it just jumps up to another value within that same time frame. So like at 1 second it's 0, but it jumps to 2 volts, like you would see in a square wave. Let's suppose that happens. So you have 0 amps, and like a square wave, it jumps up to 1 amp or some value. It doesn't even matter what value it is. It jumps in the same moment in time to that other value. That would be an instantaneous value change, which mathematically would create an infinite voltage drop according to this equation. And this is not possible with voltage. So you can't have an infinite voltage drop with just a small instantaneous change. So that means that voltage has to be finite. So my little joke here is that maybe for teleportation of matter, like in Star Trek, it's possible to have instantaneous, transfer of energy from one place to the next. But again, that's only found in science fiction. For now. So when you guys figure out how to do it in the future, my time is over. So we just showed, let's read the slide. We just showed that the current in an inductor must be continuous for all time. Okay. This means that the voltage must also be continuous for all time. Is that true or false? Okay, the answer there is false. Why is it false? Right. This is what's called a non sequitur in logic. So let's look at this non sequitur. Since we know that current must be continuous, does not mean that voltage has to be continuous. So the short answer is no. Right. So this is false. So if you remember one case or one incident, remember that you can have 0 voltage for a constant current. You can have a constant current value and still have 0 voltage. Because remember previously we were looking for a change in current that led us to a 0 voltage. Okay, so I'm going to give you a warning before I cover this slide. You can skip this slide if you're not familiar with calculus. But if you are planning to take calculus, learning electronics and how we apply calculus to electronics is a great way to actually enhance your mathematical skills in calculus. But again, you are not really responsible for the slide. But for those of you who are interested, let's go ahead and cover this. Right? So for this slide, I will describe what is happening to the equation and break it down into algebra. So you will, and I love doing this. Anything you do in calculus, you can do in algebra. It's just that calculus gives you a shortcut. So you will only be responsible for the final equations that we derive in this lecture. You don't have to derive or do any of the calculus here, even for the problems. So here we have the basic formula for voltage drop across an inductor. Rearranging the equation, we go from the top left equation to the top right equation. The middle function, which is the middle line in this slide, is something called an integral, if you're not familiar with integral calculus. So if you integrate a derivative with respect to the function, they will essentially cancel out and leave you with the function dependent variable, in this case, I of t. So if you're integrating something with respect to t, which is a derivative of something with respect to t, the derivative and the integral are basically going to cancel out, and you're left with just the function, the algebraic formula, basically, which is what we see on the left side of the equation. So the integration on the right side is called integration by parts. For those of you, anyone taking Cal 2 or taking Cal 2, and you get the function on the bottom right side of this slide. Okay. But I'm not even going to make you do that bottom equation. It's just nice to know where these electronic formulas come from. And here we are. Okay, inductor, power, and energy. So when discussing power and energy for an inductor, it doesn't change the basic formula for power in electronics, being that power is equal to V times I, just the way we studied for resistors. The physics of it has not changed. We're just now modifying our formulas to include time-dependent variables versus these static numbers. So now, since we are working with time-dependent elements, we can rewrite the formula as P of t, which you see up there, which is equal to V of t times I of t. And that's the way you would actually say that equation. You can see that the top line with the initial equation for power, right? Integrating the power equation for an inductor yields the energy equation. So we know what we knew what the power equation was for an inductor. So we integrate, you get the energy equation, and again, you're only going to be responsible for the final formula on this page for energy being W of t. Again, this is time dependent energy with respect to time. So W of t is equal to 1/2 times the inductance times I of t squared. And that's pretty straightforward if I ask you for calculating those values on a time-dependent function. But it's good to know for next semester because we will be working with only time-dependent functions next semester. So again, just a little recap on definition. If we haven't proclaimed this yet, inductors are energy storage elements. And inductors and capacitors are actually talked about together because capacitors are also energy storage elements. Except inductors use magnetic fields. An inductor can store energy and release it at a later time. All right, slide 2. So again, this is going to be a straightforward question, and you could get something like this for an exam, and this is as complicated as something like this will get. We're going to get more complicated, but just on the concepts that we covered so far, using the equations, this is basically what we would get. So suppose the initial current through a 2 millihenry inductor is 1 amp. The initial energy stored in the inductor is, and again, you can use the equation that we studied for energy in the previous slide to just plug and chug some numbers, and you should come out with 1 millijoule. But I would recommend that you practice plugging in those numbers so you can actually practice the calculation. We are on slide 11. Okay, another warning. So again, I'm just going to make sure I re-emphasize this. I will not give you a problem requiring you to perform a derivative. So you can skip to the next slide right now if you want. But again, this is the wonderful chapter description of inductors. So for those of you who want to follow this, continue listening. Now for this example, we are given the current source to be a specific function of time. Let's answer these following questions, and they're actually there on the slide. First, for the time equal to 0, which is the first condition in that little greenish bluish box, plugging this number into the exponential yields that value to be 1. So this leaves the whole function of the current to be in that equation 8 minus 8, which is there in the middle of the slide. This says that at time 0, the value of current remains 0 for no instantaneous change being predicted mathematically. Therefore, we can say it's continuous. Right now, I feel like the guy from The Princess Bride who just does that whole confusing, if the poison is in your cup, then you would know you... Yeah, okay. Somebody watch The Princess Bride, you know what I'm talking about. So, we know the formula for V of t equals inductance times d of I of t over dt. Right? So here we just substitute the function for I of t into the formula and take the derivative using the chain rule, for those of you who know the chain rule in Cal 1. So once you derive the voltage formula, you plug in 0 for the t variable. So if the value is not 0, then this function shows that the voltage is not continuous. Remember that we said that this is okay for voltage. There we go. So continuing from the previous, we substitute the functions into the power formula. So in other words, P of t is equal to V of t times I of t. This becomes a simple algebra problem with exponents now. So follow the rules of exponents for combining terms until you simplify the equation. Go to the next slide. So the energy formula for inductors is a little more straightforward. We have an algebraic formula to plug numbers into now. In this case, we know the relation of energy to inductance and current. And the author mentions that if you want to find the maximum energy, to take the derivative and set it equal to 0. Again, I'm just going to keep giving you a little bit of mathematical depth to what's going on here in electronics. So let's think about what that means, what the author is saying. If you take the derivative of a curve and find the point at which the slope is 0, that means that that's the point where the top of the curve has no slope. That's the only place it can have that. So remember that a derivative is the tangent of the curve. So basically by saying that we take the derivative and set it equal to 0, we're finding the point where that curve doesn't go any higher. The slope is 0. So that has to be the maximum point. I think that's pretty cool. That's actually, for those of you going into engineering in the future, that's a very useful tool to use for looking at derivatives and looking at where the slope is equal to 0 to find the maximum of anything. Okay. And again, if we have inductors in series, we connect the voltage drops across the inductors to equal the total voltage, just the way we would in resistors. There's a little lag here when I click the slides. So current through inductors in parallel, we find the same way again that we find current through resistors. The physics of the circuit configuration is still the same. The voltage drop across a parallel network has to be the same all the way across, just the way we would in a resistive network. Okay. So this slide says find the equivalent inductance for the circuit below, assuming I1 is 6 amps, I2 is negative 3 amps. So this is, now we're looking into circuits that you're more than likely going to see on your next exam. This is pretty straightforward. I'm sure that everyone here can give me equivalent inductance of the entire circuit, either both the parallel network and that series network. And so probably will give you one like this in your next exam. So this circuit is something you're going to see. Finding the total current is the same formula for resistors. So we have the 6 amp and the negative 3 amps through that parallel network. And then we know when we look at a parallel network that we add the individual current flows, and that gives you the total current running into that entire network. So again, 6 amps and negative 3 amps, that gives us an equivalent of just 3 amps. So I of t equaling 3 amps in this pure inductive network. We can already tell that one of the options gives us 3 amps as part of the answer, so we kind of already know that C is going to be the answer. But don't leave it there. Calculate the inductance, the equivalent inductance as well. Calculate the parallel network and then add them together with the 240 millihenries that's in series with it, and you should get 270 millihenries. So calculate both parts to be thorough so you make sure you understand the entire question. So you know how to calculate inductors and capacitors in series and parallel to find equivalent inductance and capacitors. And again, a little bit of summary. There we go. You should be able to see that. So we know what the symbol for an inductor is. We know that the units are in henries. We have what's called the describing equation, which is a derivative. You're not going to be responsible for that. We have other equations to determine what current is from that voltage equation, which is that next line. You're not going to be responsible for that. You do need to be responsible for the concepts of the initial condition, I of t naught, And those will actually be given to you. So I'll give you what the current is in your problem, what I of t naught is equal to when t is less than 0, and what I of t is equal to when when t is greater or than equal to 0. So behavior with constant source. So again, if I of t is equal to I, b of t is equal to 0, that's equivalent to a short circuit. And then the continuity requirement. I of t is continuous, so b of t must be some finite number. You can't have an infinite voltage. Power equations. I'm not going to require you to do anything more than that first half of the power, where it's P of t is equal to V of t times I of t. You're not going to have to do any derivatives in other words. But if you do have the current function and the voltage function, I do expect you to be able to use algebra to actually multiply those two functions together to give me a new function for power. And we'll do some examples of that in class, where I'll try to find something, some problems to assign you. The energy equation, this is something that I expect you to be able to comprehend. So it's energy, which is using the symbol W of t, is equal to 1/2 times inductance times I of t squared. Again, initial energy equation is something I would expect you to be familiar with. The only thing between the initial energy and the energy equation is that we're looking at the initial energy at, in this case, let's just say it's time 0. But it may not always be time 0. It could be 1 second after you turn on a switch, and that's the initial time when you start measuring. It's just whatever initial condition it is for initial energy. You're not going to be responsible for trapped energy, but you are going to be responsible for being able to calculate series connected inductance to find out what the equivalent inductance is, and you will be responsible for knowing how to calculate equivalent inductance when you have a parallel network, or a series parallel network combination is probably what I'll give you. And that concludes this lecture on inductance. The next one I will have ready for next Monday, which will be capacitance, and we're going to cover basically the same thing we did here, but with respect to capacitors. Following that lecture will be amplifiers, which will be the third week, and then we will have one final Monday to do a review for what's going to be on the written exam for the finals. So we have 4 weeks left. Capacitors. No, 3 weeks left. Including this week, it's 4 weeks. So we have capacitors, we have operational amplifiers, and the very last week we can use it to review review anything from inductors, capacitors to op amps. That's it. Enjoy.